speed of light, 186,000 miles per second, is just incredible. I mean, if light traveled in a circle around the Earth, it could circle the Earth 7 times in 1 second. That's an incredible speed.
That incredible speed is the first thing that one encounters when confronting the phenomenon of light. To say it is fast is a huge understatement. Clifford Johnson is a physics professor at the University of Southern California. He is an avid cyclist. Whilst circling a track, he tried to work out how long it would take him to cover the same 186,000 miles that light covers in 1 second.
To travel the distance that light moves in just 1 second, it would take me 22 months on a bike moving at 12 miles an hour, cycling 24 hours a day.
But the speed of light, in relation to the speed of life, makes our world work in just the way we've come to expect.
One of the beneficial effects for humanity of having the speed of light be as fast as it is that what you see is what you get.
Light speed makes everyday experiences virtually instantaneous. If a light bulb goes on, you see it straight away. Anything that happens around you registers immediately. And certain experiences make it crystal clear that light travels faster than anything else, including sound.
One interesting consequence of the great speed with which light travels is that you see a flash of lightning essentially instantaneously, but you hear the thunder only later on.
But light speed has its own limitations when put into the context of something as large as the universe.
We think that the speed of light is unimaginably fast on a human scale. However, in astronomical terms, it's actually kind of pokey.
And so it's ironic that when the Apollo spacecraft blasted into space, traveling at what seemed an amazing 25,000 miles per hour, the speed of light proved frustratingly slow when the time came to talk to the astronauts 236,000 miles away on the surface of the moon.
So when the astronauts were on the moon and people asked Neil Armstrong, "Hey, Neil, what's it like up there?" Several seconds went by between the question and Neil Armstrong's answer.
Neil, this is Houston, radio check, over. All right, Houston, loud and clear. Roger, out. Loud and clear, Houston. Roger, Buzz.
And those several seconds were not because he was thinking about the answer, but rather because it took 1.3 seconds for the signal traveling at the speed of light to reach Neil from mission control, and another 1.3 seconds for his reply using radio waves to come back. And that's 2.6 seconds without even thinking.
Okay.
The 1.3 seconds it takes light to travel from Earth to the moon is rather insignificant when compared to other celestial bodies. Light from the sun, for instance, takes more than 8 minutes to get to Earth.
If the sun were to disappear right now, if the sun were to suddenly vanish, it would take 8 minutes before we would even feel the shock wave and see the effects of a disappearing sun.
Asked a question, how can you as astronomer really comprehend these vast distances, these huge numbers? And the answer is, I can't. The human brain really doesn't wrap itself around numbers that big. Occasionally, I actually write out how many zeros there are in kilometers from here to a galaxy, just to see how huge that number is. But in reality, of course, as astronomers, we would be spending all day writing zeros unless we came up with a better unit to use. And that's what a light year is. A light year is approximately 6 trillion miles. It's the distance that light travels in 1 year.
Using light years to describe distances opens up another dimension of light speed's character. If one were to think of Sirius, the brightest star in the sky, it is 8.6 light years away. That means we see it not as it is today, but as it was 8.6 years ago. We see the bright star Vega as it was 25 years ago, and the red supergiant Betelgeuse as it was about 500 years ago.
It's a wonderful gift of nature that because it takes time to travel, we're able to look back in time. The further out we look in distance, the further back in time we look. We would have no idea what our cosmic history was if the speed of light traveled instantaneously.
Space itself, then, is the exception to the rule. It can expand faster than the speed of light. But everything inside it remains bound by Albert Einstein and his theory of relativity.
Albert Einstein is the cop on the block. You cannot break the light barrier. We physicists can accelerate particles to 99.9999% the speed of light, but we have never, ever broken the speed limit.
For most of us, light seems simple and uncomplicated, a quality of nature by which we see the universe. Under the scrutiny of science, however, it becomes strange and bizarre.
Light is such a common thing in our everyday experience, and yet we have very little understanding of it, really. It's very weird. The speed of light is something that the entire universe bends around to accommodate.
We can begin to understand why the universe bends itself around light speed by joining the physicist Clifford Johnson at a cycle track. Here, a tennis ball will compete against a beam of light.
If I throw an ordinary object like a tennis ball, I can throw it at a given speed, and it'll go a certain distance.
This is the path of the tennis ball as Johnson throws it while in a stationary position. It lands roughly halfway down the track. Then he throws the ball again, but this time from a moving bicycle. The results are different.
If I throw the tennis ball at that same speed while riding the bike, it'll go faster because it's the speed of the tennis ball plus the speed of the bike, and so it'll go further.
By comparing the two throws, the difference is clear. The ball goes faster and further when thrown from the moving bike. It makes perfect sense. But now, light is put to the same test, using the bike's headlight instead of a tennis ball.
If I'm standing stationary and I switch on the headlight of the bike, that beam of light that comes out of the headlight comes out at the speed of light. No other speed but the speed of light.
Imagine the beam was slow enough for us to actually see its motion down the track. Its position can be noted just a brief moment later. Johnson then switches on the headlight whilst riding the bike. The unexpected happens. In that same moment of time, the light travels exactly the same distance as before.
Unlike for the tennis ball, you don't add the speed of the bike to the speed of the light. The speed of light remains the speed of light.
The two light beams travel the same distance because light speed is constant and independent of the source's motion. It may fly against intuition, but it is a fact of nature. Every beam of light in the universe travels at the same speed in empty space. It doesn't matter how fast the star or comet or galaxy that emits it is moving. After scientists discovered this fact at the end of the 19th century, Albert Einstein worked on the mathematics and developed his special theory of relativity. Constant light speed was at its center.
A great example of Einstein's special theory of relativity and the fact that clocks that are moving relative to you run more slowly than your own clock, which is at rest, is the GPS system.
The global positioning system lets us drive our cars without getting lost.
Turn right.
GPS begins with a network of 24 satellites, orbiting the Earth 12,500 miles above its surface. At any one time, the device in your car receives signals from at least 4 satellites. It compares their light speed travel times in order to calculate an accurate location on the ground.
Drive 500 feet, then turn right.
The whole thing depends on super accurate clocks. And when the engineers designed the system, they knew the satellites would be orbiting at nearly 7,000 miles an hour. This speed is enough to slow down their clocks by a tiny fraction of a second. The engineers factored all the relativistic time differences into the system, which gives it impressive precision. The speed of light may be a constant, but only in the vacuum of space. When light moves through things, like glass or fluids, it slows down appreciably. If it didn't, then things like telescopes and human vision would be impossible. Therefore, in a universe where light moved at the same speed through all materials, we would know very little of the world around us, because we would only see vague blobs of dark and light. That's because our eyes depend on biological lenses to focus images onto our retinas. Just like lenses made of glass, they work because light slows down as it passes through them.
So as you try to go faster and faster and faster, you actually get to a point where it takes more and more energy until it's an infinite amount of energy to go the speed of light. That's impossible.
It means that travel at light speed is also impossible. And what if science ultimately proves that the light speed barrier is unbreakable and that star travel is impossible? Then we would be forced to concentrate our efforts, technology and wisdom on preserving our world, Earth, as it continues to shelter us and take us on our journey through the universe.